We present a novel method for encoding and generating dynamic agent-scene interactions in human activity spaces. We train our generative model on videos of people interacting with real objects. The model learns the causal dependencies and physical constraints between individual actions and can be used to generate new interaction sequences, and thereby enables the previously unseen capability of representing interactions in a variety of applications, including future prediction, animation synthesis, and semantic planning for a real robotic agent. We introduce a novel representation for interaction, the so-called action plots, that encode interactions as a set of discrete actions. Each action in the action plot can be seen as a keyframe capturing a unique phase of the interaction. This discretization allows us to focus on the combinatorial nature of human-object interactions, while abstracting away the complexity of spatio-temporal transformations. An action plot is a sequence of actions defined as discrete operations. This allows us to leverage a novel neural network architecture to learn the causal dependencies of these actions and to use it to predict and generate interactions. Additionally, we define a motion model based on Gaussian mixture models to learn and predict characteristic properties of the motion patterns of objects. We jointly use the observed object locations in our dataset, their relationships, and their movement distance to train the model. The lower right illustration shows the final distribution for querying new positions for a few objects. We use state-of-the-art computer vision techniques to track hand and object motions, as well as their state changes. This allows us to capture human-object interactions simply by observing videos of people performing regular activities. Additionally, we automatically segment our videos based on the method of Lee et al., which allows us to infer the type and duration of the performed actions. Using the action plots not only enables the efficient learning of interaction sequences, but also to represent and synthesize interactions for a variety of applications, including future prediction, animation synthesis, and the semantic planning of real robotic agents. Our action plot RNN focuses on learning causal dependencies of the observed actions, not on individual objects. We can then use the observed interactions of a few objects to learn action patterns to animate several shapes. Moreover, we can transfer the learned interaction sequences to new scenes, while also respecting their individual constraints. The scene on the left only shows objects and their interactions. The two scenes on the right also contain static objects that constrain the motion paths of the interacting objects. All scenes use the same action plot. Our model allows to continue captured videos by predicting plausible subsequent actions. Here we show the captured video, the reconstructed synthetic scene, and two generated sequences. By capturing videos of humans interacting with real-world objects, we can learn and generate plausible interaction sequences. Here, we show the video capture, the reconstructed sequence, and a new generated set of interactions. Given the scene state, the action plot RNN allows us to predict the next plausible actions of a scene. Here, we show how this can be used to anticipate interactions with objects a few frames in the future. Interaction plots are a general means for representing plausible action sequences. Here, we show how predicting action sequences can be exploited for semantic planning in smart and reactive environments. We design a smart cup with a differential drive robotic base. To perform motion planning, it is crucial to understand the scene. Moreover, for semantic interaction planning, plausible future actions also need to be predicted. For example, when our pipeline predicts a pouring action, the smart cup reactively comes near the bottle.